Welcome to this Indeed journey, where we explore the science and engineering behind sending a spacecraft to Mars and bringing it back to Earth. This script is inspired by the article Journey to Mars, the Physics of Traveling to the Red Planet by S. Dinner and J. Bergeret. Over the next 5 minutes, we will break down the concepts, challenge, and calculation involved in the interplanetary travel. Now, let me introduce my group member. Our group leader, Tan Kaming, followed by CHUAN, THENG, and myself, LEONG.
So, in order to travel to Mars, we need to use a method called the Hoffman transfer orbit, which is an efficient way to move between two planetary orbits using the least amount of fuel. So this involves two thrusts. The first thrust is to push the spacecraft out of Earth's orbit and into an elliptical orbit around the Sun. And the second thrust is at the elliptical orbit's apopapsis to adjust the spacecraft into Mars orbit. And we use the following constants, which is the radius of Mars, the radius of Earth, the distance of Mars' sphere of influence, and also Earth's sphere of influence. We note that 1 AU is 1 astronomical unit, which is the average distance between the Earth and the Sun, about 150 million kilometers. And we use the Hughes sphere model to calculate the gravitational sphere of influence, which is the region around a celestial body which it dominates the motion of satellites over the gravitational influence. Let's make some assumptions about our calculations. So the first assumption is that both orbits are circular, and the second assumption is that both orbits are coplanar for simplicity in our calculations. So we use three equations in our calculations. The first is Rees-Viva equation, the second is the total energy of an orbiting body, and the third equation is the period of a body moving around the Sun. Now that we have our parameters and equations in place, we can finally move on to calculate the transfer orbit, which is an ellipse with an apogee radius of 1.52 AU and a perigee radius of 1 AU. And we can take the average of both of these radius to get our semi-major axis, which is 1.26 AU. And we can substitute that into our third equation, which is the period of a body around the Sun, and we can get P equals to 516 days. And since the path is half of the ellipse, we divide that value by 2 to get 258 days. And next, we use the Rees-Viva formula and substitute the values again to find the apogee velocity to be 21.5 km per second, and the perigee velocity is 32.7 km per second relative to the Sun. The orbital velocity of Earth is now 29.8 km per second, and the orbital velocity of Mars is 24.1 km per second. We note that the spacecraft, to reach Earth's sphere of influence, it will take about 1.5 days. Hence, the launch date should be about 1.5 days before the actual departure date. And now we calculate the transfer to Mars. There are three steps involved. So the first step is that the spacecraft must reach an escape velocity of 11.2 km per second to escape Earth's gravitational pull. The second step is, since the spacecraft and the Earth are moving at the same velocity relative to the Sun, the spacecraft is then accelerated by 2.9 km per second to reach a perigee velocity of 32.7 km per second relative to the Sun. The spacecraft's velocity relative to Earth is 14.2 km per second. The spacecraft will then follow the elliptical Hoffman transfer orbit. The third step is the spacecraft approaches Mars about 256 days later. The orbital velocity of Mars is 24.1 km per second, which is higher than the spacecraft's approach velocity of about 21.5 km per second. Therefore, the spacecraft should arrive just ahead of Mars, allowing the planet to catch up with it. The relative velocity will then be 2.6 km per second, and retrograde rockets will be engaged to achieve this velocity, as the escape velocity from Mars is 5.1 km per second. The total velocity for the trip will then be 16.7 km per second.
There are two methods for the spacecraft to return to Earth. Method 1. Hoffman transfer. The spacecraft will remain on Mars for 458 days to ensure that Earth and Mars are positioned properly for the second Hoffman transfer model. Step 1. To escape Mars' gravitational pull, the spacecraft will leave in the opposite direction to Mars' orbital motion. The spacecraft velocity relative to the Sun will decrease from 24.1 km per second to 21.5 km per second. This requires a total change of 7.7 km per second. The spacecraft then enters an elliptical transfer orbit. Step 2. The spacecraft will approach Earth in about 256 days with a velocity of 32.7 km per second, which is 2.9 km per second faster than Earth's orbital velocity. Earth will then pull the spacecraft in just as Mars did. Without using retrograde rockets, the spacecraft would fall into Earth with a velocity of approximately 11.6 km per second. This is slightly higher than the escape velocity of 11.2 km per second. Thus, the change in velocity required is about 11.6 km per second, and the energy budget is 2 times 10 power of 8 joule per kilogram. The features of Hoffman transfers, it used the lowest energy and the total time used is 2.7 years. The second method for the spacecraft to return to Earth is modified HOT trajectory. In this case, the spacecraft lands on Mars and stays there for about 30 days. The spacecraft then returns to Earth via a trajectory with higher eccentricity. It approaches Mars along the regular HOT trajectory but intercepts Mars orbit 30 days earlier and then leaves Mars at the aphelion point. The return orbit has a perigee of 0.42 AU, ensuring that the spacecraft will reconnect with Earth in about 235 days. Step 1. The spacecraft approached Mars using the regular HOT trajectory with the same change in velocity of 16.7 km per second, but arrives at Mars 30 days earlier. Step 2. The spacecraft leaves Mars in the opposite direction of its motion around the Sun, overcoming the planet's gravity and slow down to 21.3 km per second. This requires the change of velocity is 7.5 km per second. Step 3. As the spacecraft approaches Earth, its velocity will be 32.8 km per second. It needs to slow down to 29.8 km per second, requiring a change of velocity of -3 km per second. To overcome Earth's gravitational pull, an additional velocity of change of -11.2 km per second is needed. The total change in velocity for this step is 14.2 km per second. The total change in velocity for the entire trip will be 38.4 km per second, and the energy budget is 2.3 times 10 power of 8 joule per kilo. The features of the transfer: more energy expenditure and less time is required. This video is presented by Group 18. Thank you for watching the video. Hope you enjoyed.